Okay, for today, I think we'll just do a brief overview of scientific notation and some balancing chemical equations. We're probably going to get back to school one of these days. We'll keep our fingers crossed that it's tomorrow. So, for instance, if we're looking at 3 million, okay, I think that's even 300,000, okay? If we put 0.00 there, if we need to convert that to scientific notation, even though we're moving to the left, it's a positive number, so we would change that to 3.00 times 10 to the fifth, because we moved it over 5 times. 1, 2, 3, 4, 5. So there's our decimal place there. So once we do that, that is a positive value. And of course we can go backwards again and say we're going to change that back to 300,000 and go 1, 2, 3, 4, 5. The reason we want to bring it up that way is because if we had such a small number, perhaps measured in moles, and maybe that is something along the lines of 0.015, okay? If we wanted to change that to a scientific notation, we're going to go to the right, and it has to be a number between 1 and 10. Just like this has to be a number between 1 and 10, which of course 3 fits that criteria. 1.5 would also fit that criteria. We're moving to the right 2 times, and upon doing so, that would be 1.50 times 10 to the negative second. Okay? Because since this value is lower than 1, it has a negative value. Okay? Because if we're going to change that from scientific notation and move to the left, see, since this is greater than 1, you're moving to the left, it's got a positive value. Here, we're taking this and we're going to the left, but it is less than 1, so that's why that ends up being a negative value. Okay? So, and that would be the same even if you're dealing with such a small number like this. Maybe it's 3.79 times 10 to the negative sixth. Okay? So if we are doing that, okay, since it's to the negative sixth, this value is actually less than 1, and that would give us a value of 0.0000379. I think that's 6 times. 1, 2, 3, 4. Oops. 1, 2, 3, 4, 5. Oh, I need to put one more 0 in there. Okay. Now I think we got 6. 1, 2, 3, 4, 5, 6. There we go. Okay. So I just was off by 1 0 in that context. All right. So that's how you actually do scientific notation. And looks like we have a supervisor coming down here. You checking up on my work? Come here. Come here. Huh? This is what I mean by my supervisor. Huh? Why don't you say hello, Dozier? Huh? So, all right. All right, I got it. Get back to work, you told me. All right. Okay. There we go. All right. I'll go ahead and hit pause. You don't need to see me erasing this. I think part of this, what makes it so tough, is we're really not covering any new content. When we were actually staying home from COVID a couple, 3 years ago, at least every day, we were probably moving forward, where that is not the case here. So, if we're going to do complete each reaction, maybe we've got lead 2, and we're going to add some chlorine to it. Okay, chlorine is diatomic in the synthesis reaction. We said this is a +2 charge. These two come together, and since this is +2, that's -1. Least common multiple is 2, so we have to put a 2 there. Then the last thing is just balance our chemical equation, which we see we've got 1 to 1 and 2 to 2. So nothing has changed. Sometimes that happens. That equation is balanced. Okay? Then we can do just the opposite. Maybe we've got some lead 2 oxide. So lead 2 oxide. Okay, so plus 2 minus 2, that adds up to 0. So if this is going to break apart like decomposition reactions do, we've got Pb plus O2. Okay, so then in this case, remember, halogens, gases are diatomic. So in this case, we've got 2 oxygens over there, only 1 here. You need a 2 there and a 2 there. So that changes to 2, 2, 1. Okay. Then let's move on to a single replacement reaction. I'm going to put 2 of them up here. Okay. And the reason for that is if we had hydrochloric acid, okay, and if we're going to add some calcium to it, and let you maybe decide or decipher what it is you think is going to arrive from that equation. And we'll go ahead and put some sulfuric acid here. Okay, and let's maybe add some, I don't know, just keep it simple, something in column 2, maybe some beryllium. Okay, so go ahead and work on that for just a moment if you so choose, and then we'll show you what the answer actually is. And I always like to ask this question of any of these subscripts here, are any of them going over to that side for certain? And in this case, actually both of these are. But it's just a coincidence that this one does. This is actually part of the formula. So we have to finish this. We've got calcium in column 2 and chlorine, so that's plus 2 minus 1. So we need to put a 2 there, and then remember, hydrogen is diatomic, so when we balance this, I'm kind of running out of space on this small board. We've got 2 hydrogens over there and only 1 here. So once we put a 2 there, I believe that balances everything. So 2, 1, 1, and 1. Then on this bottom equation, we had already established those 2 are going over there for sure. This is in column 2, just like calcium. Sulfate's got a -2 charge, so we have beryllium sulfate. And then just like the equation above, hydrogen being diatomic. Last thing we need to do is balance everything out. And looks like 2 hydrogens, 2 hydrogens, 1 sulfate, 1 sulfate, 1 beryllium, 1 beryllium. So it's actually balanced. So 1, 1, 1, and 1. Then let's go ahead and move on to a double replacement. Actually, we'll save the double replacement reactions and maybe just do a quick combustion reaction. We'll do one that's perhaps a little more difficult. So C6H14 plus O2, and that gives you CO2 always plus H2O always in a combustion reaction. Okay. The reason I wanted to pick one like this is this hydrocarbon is even. If you don't double that right away, you're going to have fits. So if we do that, put a 2 here. 2 times 6 gives you 12. So we put a 12 here. Let's not worry about the oxygens. Okay. 2 times 14 gives you 28 for your hydrogens. We've got 2 over here, so we need 14. Now your hydrogens are balanced. Now let's deal with your oxygens. 12 times 2, 24. And then 14 times 1, it gives you 14, so that's 38. So 38 divided by 2 then gives you 19. So there is your coefficients, 2, 19, 12, and 14. Okay, I think that's enough for today because I think probably spending a whole lot of time on this just really isn't a very good, let's say, maybe use of your time. So when you come to class, hopefully tomorrow, just have some specific questions that you feel you need to go over, whether it's atoms and moles, electrons with Bohr models, the configurations, the orbital diagrams, which includes the quantum numbers, the dot diagrams, then empirical molecular formulas, naming compounds, and balancing chemical reactions, which we just did, and that is where we ended with the semester. Okay, so that's all I have. We'll catch up to you hopefully tomorrow in class. We'll hopefully see you then.